What keeps a ball in motion after it is, let's say we're talking about a bowling ball. So once I get a bowling ball rolling, why does it keep rolling? Why does it keep moving? Well, we can say a couple different ways we can answer that. We could say inertia. Okay, an object keeps in motion, stays in motion, that is in motion, its tendency is to stay in motion. We could say that the lack of an unbalanced force to cause it to slow down. So it's not the fact that there's a force keeping it in motion, it's that there's an absence of force to slow it down. So we really say it's inertia. Let's say we were playing tennis, and we had a tennis ball, and we bounced off of our tennis racket. We would have to exert a force on that tennis ball to cause it to change its motion. So if the tennis ball was traveling towards us at 25 miles per hour and we wanted to change that, we'd have to exert a force with the tennis ball because the tennis ball has got inertia. Okay, we could have the same 25 miles per hour, and this time we would play tennis with an 18-wheeler. We're going to have a little bit more of a problem trying to change the motion of that 18-wheeler. Both the tennis ball and the 18-wheeler have inertia, but the 18-wheeler's got a lot more inertia. It's a lot harder to change its motion because the 18-wheeler's got a lot more of what? It's got a lot more mass. Okay, so the mass of an object determines how much inertia it has. So how much inertia an object has depends on its mass. The more mass an object has, the harder it is to change its velocity. Okay? So more massive objects are harder or lazier to speed up, to slow down, or change the direction. But inertia is not a force. It is a resistance to changing motion of forces. So normally this is when we would learn about inertia from El Nino, who is my bowling ball, which we would be driving around El Nino around a course with a broom, but we won't be doing that because of the COVID. Okay, anyway. So when we talk about forces, there's a certain notation or format that we can use. Big F for force, and then we'll talk about the type, the feeler of that force, and the dealer of that force. So the type will be gravity, tension, etc., friction, things like that. The feeler is basically the object that force is on, the object that is being pushed or pulled. Okay, and the dealer is the other object that's involved that's doing the pushing or pulling. Okay, so let's look at the first type of force, which is F sub G. Okay, so force of gravity. We're going to look at this diver, and there's a force of gravity on the diver. What's causing that force of gravity? What's the dealer of that force? The feeler is the diver. The dealer of that force is the earth. So there's a force of gravity on the diver by the earth, and that's the first force that we're going to learn about. The next force that we're going to talk about is what's called the normal force. And by normal force, I don't mean it's your average everyday normal force. It's your typical standard force. Normal in this case means perpendicular, so it's a math term. So a normal force results from any two objects that are in contact, any two surfaces that are in contact, and it's a force that is perpendicular to the surfaces that are in contact and away from that surface. So if we were to talk about the elephant and he's standing on this pedestal, there's a normal force on the elephant by the pedestal, and it would be directed up. Okay, because the pedestal is flat, like so, and so the force is perpendicular to the pedestal and away from the pedestal, so up. So there's a normal force on the elephant by the pedestal, and we're going to see the normal force all over the place. So it'll be something that's super common. And again, the normal force is always perpendicular to the two surfaces and away from it. So here, this would be the direction of the normal force. And if we were contacting this sloped surface, the elephant's paw was on this sloped surface, there would be a force perpendicular to that surface and away from it. So perpendicular and away. So here we've got a red ball on a green slope. And what would the direction of the normal force on the ball be? Okay. It would be away from the surface and perpendicular to it. So, and that would be a normal force on the marble by the ground. Okay. Now that wouldn't be the only force acting on it if it was stationary, and we'll get to that a little bit later. Now, does the elephant appear to be accelerated? No. That must mean that the forces on the elephant must be balanced. And if they're balanced, we've got to have equal and opposite forces. So if there's a normal force up, that means there's got to be a force down. What would the force acting on the elephant in the downward direction be? Well, that would be our friend gravity, wouldn't it? Okay. So if we want to show that two forces are equal and opposite and are going to cancel out, or if we just want to show that two forces are equal in magnitude, we use these little hash marks across them, and that just is me saying you don't have to get a ruler out to measure these to see if they're the exact same length. I'm going to tell you that these two force vectors cancel out because they're the same length. Okay. Third type of force that we're going to deal with is a force of tension, and it's basically anytime you've got a rope or a cable or something like that, some string, and it's always a pull in the direction of the string. So here we've got this little blue barrel, and it's being supported by the string. So there would be I call it a block, I guess, in my thing. So there's a force of tension, F sub t, on the block by the string, okay, and it's pointed up because that's the way the tension is pulling on the barrel. So here we've got a force of tension acting on these girls, okay, and what would the direction of the force of tension be on her hand? Well, it's a pull away from the person in the direction of the rope. So it would be off at this angle like so. Okay. Another big important force is friction. Friction is a contact force that results from two surfaces in contact, similar to the normal force. Okay, two surfaces in contact, but it acts opposite the motion or impending motion of this object. So this baseball player is sliding to the left, okay, and friction is acting opposite motion, which is acting to the right. So the force of friction is to the right. So using our notation, it would be a force of friction on the baseball player by the what? What would be the dealer of that force? By the ground, the dirt, the earth, something along those lines. So the force of friction on the player by the dirt. Okay, is friction changing the motion of this object? Is he moving at a constant speed as he slides into first base, or not first base, second base here? No, he's slowing down. That means that friction is not being canceled out by another force. Okay, so anyway. Now we said friction acts opposite motion or impending motion. So if this crate is stationary, its impending motion would be in what direction? Which way would it go if there was no friction? Oh, it'd slide down this slope down and to the right. Okay, so that means friction is going to act opposite, so it's going to act up and to the left. Okay. So because forces are vectors, we can add or subtract them just like any other vector. We're not going to do too much in the way of perpendicular vector addition, just kind of in the same direction or opposite direction. So if we have two forces, we can add them up, and whatever's left over, okay, because they might add, they might subtract. Okay, in this case, we're going to have these two forces that are going to subtract. And so what's left over we call the net force. Okay, anything that's left over. So if you take home $20 and you got to spend $15 on rent or whatever, what you're left over, your net pay is your net dollars is the $5 that's left over. Okay, so the net force is basically just it's the resultant. Okay, so if we had 5 newtons up and 9 newtons down, and we were to add these up and find the resultant, okay, there would be 4 newtons down, and that's the net force. The net force is the resultant of force vectors. That's all there is to it. So this is nothing new. Okay. So now if we add these two vectors up, okay, and I should have these hash marks across here. I don't know why I don't. And I've got 9 up and I've got 9 down. We add them up and we get 0. The net force is 0. What do we call forces where the net force is 0? They're equal and opposite. Starts with a B. We say that they are balanced. So these forces are balanced. Okay. What is an object doing? It's doing one of two things. Okay, if the forces on it are balanced, it's either stationary and remaining stationary, or it's moving how? At a constant velocity. So in either way, the velocity is constant. It's just depends on if it's got a velocity or not. Okay, so let's find the net force for each of these situations here. So we've got 10 up and 15 down, so my net force is going to be 5 down, okay, or negative 5. Okay. 15 up and 10 down, our net force is going to be 5 up, okay, or positive 5. Okay. Here we've got 10 down and 15 down, my net force is going to be 25 down. Okay. And here I've got 10 up and 10 down, and my net force is going to be 0. These forces are balanced. Okay, so if the forces on an object cancel out, if they add up to 0, okay, an object's velocity doesn't change. If the forces don't cancel out, this is one way of writing that. The sum of the forces do not add up to 0, so the forces don't cancel out. This is a way of saying that there's a net force. So if an object is traveling to the right and there's an unbalanced force, there's a net force to the left, okay, what does it do? It slows down. What if it's moving to the right and there's an unbalanced force acting to the right? It's going to do what? It's going to speed up. Okay. What if it's moving to the right and there's an unbalanced force up? Well, what's it going to do? It's going to speed up, slow down, or the last one is change direction. Okay. So it's going to change direction. So those are what's going on. So if the forces do cancel, an object's velocity is constant. Okay. If the forces add up to 0, an object's velocity is constant. If the forces do not add up to 0, it's going to speed up, slow down, or change direction. So back to the forces do cancel out. So the sum of my forces equal to 0. My forces cancel out. My forces are balanced. Okay. So if this object is stationary and there are balanced forces acting on it, what does it do? It stays put. Okay. If the forces on an object are balanced, its motion doesn't change. Its velocity is constant. So it'll remain still. What if an object is moving and the forces acting on it are balanced? Okay. What if I get it moving like a bowling ball and the forces acting on it are balanced? What does it do? It keeps rolling on and rolling on forever unless something causes it to slow it down, unless we get an unbalanced force. Okay. So free body diagrams, what we're going to cover lastly here. And basically they're real simple. You take an object of interest and you turn it into a dot. So here's my boy blindfolded. I don't know why he's blindfolded. He just is. Okay, and we're going to make the boy a dot, and we're going to label the forces acting on the boy. We're going to draw them away from the dot. So what's a force that's acting on the boy? Okay, well, he's on planet Earth, so we've got a force of gravity. Okay, and that's going to point which way? It's going to point down. Okay. Oh, I forgot to mention: are the forces balanced or unbalanced on the boy? Is the boy changing speed, changing velocity? No, the boy looks stationary, looks to be staying stationary. So I'd say the forces on this guy cancel out. So when we're done, all of our forces should cancel out. So we've got gravity down. Okay. So that means we need an upward force. What would be the upward force that's canceling out gravity? Why isn't he falling down? Because he's got his feet on the floor. There's a normal force. Okay. So there's a force of gravity on the boy by the earth down. Okay. The earth is, whenever we're dealing with the force of gravity, the dealer is always going to be the earth. Okay, at least if we're on planet Earth. And there's a normal force on the boy by the pillow. The pillow is exerting that contact force, and perpendicular from his feet, the flattened pillow, which is up. Okay. So now again, we don't really care where the forces are acting on the boy because we made the boy a dot. So we just need to know the direction of the force and the feeler and the dealer and the type of force. So, and lastly, what do we do to show that these forces are equal or balanced? Hash marks. Okay. So if the object does not accelerate, okay, then the forces are balanced, and we know that these hash marks indicate that these cancel out. Okay, so that is it for today. Do worksheet 4-1, and we'll see you soon.